All right, today we are going to wrap up equation writing with part 3, where we're going to focus on precipitation reaction, which are double replacement reactions, and we're going to cover net ionic equations. Both of these are incredibly important. They're explicitly in our AP curriculum, so it's something you will definitely see show up in various questions. So just to get you thinking, I have a clear aqueous solution, potassium iodide, and I have a clear aqueous solution of lead 2 nitrate. Okay, so these are both aqueous, they are both clear. If I add my lead 2 nitrate, let's watch what happens. You should see pretty clearly it turns yellow. That yellow is actually a solid that's formed from these two aqueous solutions. And this is going to get right into our precipitation reactions, give you something to hopefully think about and come back to in class as well. So let's get started. All right, so let's get working on these precipitation reactions, which are double replacement reactions. Precipitation reactions, are specifically called that because you are mixing ions that are in aqueous solutions, with the two separate clear solutions I had, and when mixed together, they are going to produce an insoluble or slightly soluble salt. Now, a big part of writing precipitation reactions are knowing your solubility rules. I'm going to expect that you are going to be able to know many of them. When it comes to AP exam, the ones that they're concerned with are the ones that are listed here. You need to know that all sodium, potassium, ammonium, and nitrate salts are always soluble. Usually if you know that rule, you'll be able to narrow down which one is your insoluble one. Here's one example of a chart that you could use to learn these solubility rules. You'll see those examples that are always soluble. That's in the AP curriculum, like your group 1, ions, ammonium, nitrate. I also think acetates are really important to know as being always soluble. You'll see some of the examples here that tend to be soluble, except when they're with stuff like silver and lead. Those tend to be ones that form insoluble salts, unless they're with these little top group. And then you'll see some down here that are always, I shouldn't say always, are generally insoluble: hydroxides, carbonates, phosphates, sulfides, except when they're with, again, group 1, ammonium, nitrate, acetates. The only other thing with this group is that there are some other exceptions as well, just to be aware of. I really like table F. That's our Regents reference table for figuring this out, so you could use that as well. I think it makes it very clear which will be soluble or insoluble. So we'll keep going back to it, because I think those charts are a lot easier to understand when we do examples with them. So this first one is just write a double replacement or precipitation reaction for aqueous sodium carbonate and aqueous calcium chloride. So I'm going to start by writing my two reactants. So sodium is +1, carbonate is -2. So my first one is going to be Na2CO3, and that's aqueous. That is going to react with our calcium chloride. So calcium is +2, chloride is -1. So this is going to be CaCl2, and then this is aqueous. Okay, here are two reactants. So now we're going to make the two products. So remember, in a double replacement reaction, we're going to have one component of each compound switch. So we are looking to switch the metals between them. So sodium is going to come over with chlorine, calcium is going to go over with carbonate. So when we write this, I'm going to have Ca and then CO3. Calcium is +2, carbonate is -2, so I need 1 and 1. Okay, I'm going to just put parentheses here. Then I have sodium that's going to be with chloride ions. Now be careful. Na is +1. Chloride ions are -1, so I only need one of each. Remember, anytime you make a new compound, you need to check charges. Do not base them from over here. And then we're going to put parentheses here. So that would be the first step. Just get the two formulas down. Then you need to come up with their phases. So if I look at, let's just say this chart up top, I have carbonate. So carbonate, unless it was with group 1 or ammonium, which it isn't, is going to be insoluble. If it is insoluble, we put an S there to mean solid. So that is our solid because it is insoluble. Okay, if I look at my chloride ions up here, chloride ions tend to be soluble. It is not with any of these exceptions. So this will be soluble, so this will be AQ. Okay, so that's how we get those two phases. Okay, you're going to get very comfortable with a lot of the common examples, so you'll be able to do that on your own. And then just to balance this out, we need to put a 2 in front of NaCl. Okay. Then we're going to write a double replacement reaction for aqueous ammonium hydroxide and aqueous lead-2 nitrate. So I'm going to start with my two reactants. So I have NH4, OH. NH4 is +1, OH is -1. This is going to be aqueous. Plus then I have lead-2 nitrate. Okay, lead is +2, nitrate is -1, so this has to be a 2 to balance out the charges. And then we're going to go and write our products. Okay, here we're going to have lead bonding with hydroxide now. So Pb, it is going to keep its +2 charge. Okay, and then it's going to bond with hydroxide, which is -1, so we need a 2 here. Okay, then I'm going to take my ammonium ion and react it with, or have it with nitrate. So this is going to be NH4, which is +1, NO3, which is -1, so I just need one of each, and I'm going to have parentheses right there. All right, if I look up here, hydroxide, okay, tends to be insoluble unless it was one of these exceptions. Lead is not, so that is going to be my precipitate or my solid. Okay, you'll sometimes see precipitate is PPT. Okay, that's your precipitate. You definitely need to be able to pick that out and know that term. And then over here, nitrate, remember, is always soluble, so this is going to be AQ. And then finally, just check for everything to be balanced. I would need to balance out my hydroxide, so this would need to be a 2. And then balancing out my ammoniums and nitrates would leave me with a 2 there. So those are precipitation reactions. All right, so let's move on to writing net ionic equations. So this is an important part and something that's going to show up all year, and you will probably see in May. Because it's explicitly right in our AP curriculum. So you need to be able to write balanced molecular equations, which doesn't mean that they're just molecular compounds. It just means in the molecule form or the compound form. So it can include ionic compounds, a complete ionic or total ionic equation, and then these net ionic equations. So there's just different forms to kind of depict the reaction that may be taking place. So let's look at this first example and jump right in. This was a reaction from our double replacement reaction. So what we're going to do is we're going to write the complete or total ionic equation, and it's going to involve these aqueous compounds because when they're actually mixed in with water, they don't stick together as a compound. They're actually dissolved into the water, so they're floating around as their individual ions, and that's what we want to represent. So we're going to start with sodium. We have, I wanted to make sure this was balanced. We're going to have 2 of them. So that 2 represents 2 sodium ions. So we're going to place that as a coefficient out in front. So 2 Na+, you can do plus or 1+, and then AQ. Then I'm going to take the negative ion. Now here, this is carbonate, CO3. Those polyatomic ions are going to stick together. So this 3 does not get put out in front. It stays right there with the oxygen. So this would be our carbonate ion, CO3, 2-, its charge, and then showing that it's aqueous. Then we're going to move on to the next aqueous reactant. So we have 1 calcium here, so it's going to be Ca. It has a +2 charge. And then we include the aqueous. Here, this 2 is representing 2 chloride ions. So that 2 will now actually go out in front. Cl, 1-, and then showing the AQ. So then when we go over to the product side, this is where you have to be really careful. So, excuse the bell. Here we have calcium carbonate. That is a solid. That is going to stay together as a compound within the crystal lattice of the solid. So we don't separate it. This will also be the case if you have a gas that is a product. So that is going to be CaCO3, the little solid next to it. So keep it together. And then aqueous, this is going to get broken apart into aqueous ions. This 2 becomes important. That applies to everything attached to it, the sodium and the chloride ions. So this is going to be 2Na, 1+, see that over there? Went over a little, I'll put it below. You have 2 chloride ions, aqueous. So when you write a total or complete ionic equation, I'm looking for all the aqueous ions, their charges, that it's balanced still, that it's all there. When we go to do the net ionic equation, this is a lot of information, the complete ionic equation. The net ionic equation is really showing the chemistry that's actually going on. That's because the complete ionic equation has what are called spectator ions. So in this reaction, spectator ions is the sodium ion because it is an aqueous ion on the left and it is an aqueous ion on the right, or the product side. The other one is going to be the chloride ions. Okay, so what that means when we get to the net ionic equation is that those are just hanging out the whole time. Think about if you're a spectator at a football game. You're not actually playing in the football game, right? You're just watching it. That's what these ions are doing. They're there, but they're not actually participating in the chemistry that's going on, the reaction that's going on. So you don't have to do this on yours, but I'm just going to show you. I'm going to take out the spectator ions. So that is the sodium ion on the reactant side and the sodium ion on the product side, both of them. And then the 2 chloride ions on the reactant side and the 2 chloride ions on the product side. What you are left with is that net ionic equation. It is always going to involve the ions that form that precipitate. Okay, so over here, and I usually always like write the positive one first. I have my calcium ion plus my carbonate ion is going to make the calcium carbonate solid. Okay, that is my net ionic equation. Okay, a lot of times you don't need to write this complete ionic equation. You want to be able to focus in on your precipitate, find the ions that are going to produce that precipitate, and then write the balance equation. So you may need to work on just jumping to that. All right, let's do another example in case you need it. So here we're going to write the complete ionic equation. Again, everything that is aqueous, I'm going to break apart into ions, and then that solid I'm going to keep together. So here I have, in this example, I have 2 ammonium ions, which each have a 1+ charge. And then remember that 2 also applies to hydroxide. I have my 2 hydroxide ions. And then moving over here, I have 1 lead, Pp, that has a +2 charge based on that formula. And then just be careful here. NO3 is our polyatomic nitrate ion. I have 2 of them, so that 2 actually will, in this case, go out in front with its charge. Okay, that should be my complete reactant side. Over on the product side, again, keep that solid together. Do not break it apart, but I do need to break apart the other product, my ammonium nitrate, into 2, keep writing ammonium wrong, NH4, 1+ ions, and the 2 NO3 or nitrate ions. Okay, again, every ion has its charge and showing that it's aqueous. This is still balanced based on the balance equation that we started with. So just to review, those spectator ions in this case would be my ammonium ions and my nitrate ions. Okay, I'm crossing them off at both sides, which should make sense because here is my solid precipitate. So what should be left are the ions involved in forming that. So I'm going to write my lead 2+ plus my 2 hydroxide, forming my lead 2 hydroxide precipitate. And that would be my net ionic equation. All right, I did want to show you that this net ionic equation does not just apply to double replacement reactions. Some students, because we practice them so much with double replacement reactions, kind of get stuck on that it only applies to it. But you can do this with something like a single replacement reaction as well. So with this one, here's our reaction. Remember what I said before, solids, just be careful with. And then it's the aqueous compounds in this case that we're going to have to break apart, showing what they look like in solution. So for here, I'm going to have Mg solid. I'm going to break apart my tin 2 chloride. So I have SN2+ aqueous plus my 2 chloride ions, aqueous. Okay, that would be my reactant side. On my product side, I'm going to have my magnesium ion, which is group 2, so it's +2. My 2 chloride ions, and then the solid tin. So when we talk about spectator ions, be careful here. Solid magnesium on the reactant side and a magnesium ion on the right-hand side, it has changed, okay? And we will get to that eventually when we talk about redox reactions, but that's a difference. The only thing that stays exactly the same on the reactant and product side are those chloride ions. So the chloride ions are the only spectator ions in this single replacement reaction. So when we go to write our net ionic for this, we're going to have the solid magnesium with the tin 2 aqueous ions producing the magnesium ions, and then the solid tin. And that would be my net ionic equation in this case. So I just wanted you to see one of those. This will kind of come back up again when we do, again, redox reactions and we talk about oxidation reduction, but I wanted you to see it and recognize it as a net ionic. All right, well, that's it. So definitely make sure you spend some time working on these. This is a huge concept that we need to really nail down before we move on too much further.